Right. Okay. We're online. So welcome. Good afternoon. Good morning, wherever you are. It's next Tuesday. This Tuesday on Warsaw Observatory, Warsaw University Astronomical Observatory seminar series. We have a guest from the US, Kevin Burdge from California Institute of Technology called Caltech. However, I just learned that Kevin is already in MIT, where he did his undergrads. He then did his PhD at Caltech, and he is now continuing at MIT studying physics and merging difficult fields together, astronomy and physics, teaching physicists how to do proper astronomy, especially in the topic of gravitational wave. So, Kevin, please.
Thank you. All right, as just mentioned in the introduction, I'm currently a finishing graduate student at Caltech. My PhD advisor was Tom Prince, who was one of the former co-chairs of the International LISA science team. And so a lot of my work has been focused on LISA-related gravitational waves. For those of you who don't know what LISA is, don't worry, I'm going to give a thorough introduction. And so what I'm going to be talking about is the core of my PhD work, which has been basically using photons to discover LISA detectable millihertz gravitational wave sources. And so I'm going to give a little bit of a general introduction here to gravitational waves. So first off, what are gravitational waves? Well, basically, gravitational waves are propagating perturbations in the space-time metric that are generated by a third time derivative of the quadrupole moment of a mass distribution. The type of mass distribution, which will give you a time-evolving quadrupole moment like that, one of the best happens to be a binary system with two stars orbiting each other. And in particular, the gravitational waves we are most sensitive to and can actually detect tend to be higher frequency gravitational waves because our frequency sensitivity with current detectors mainly operates in high frequencies, but also because the strain amplitude of gravitational wave sources at high frequencies is much larger than low frequency sources. So I haven't actually told you what the sources are yet. In particular, the sources involve two very, very dense objects orbiting each other in a short orbital period. And the examples that we've detected are binary black holes and neutron stars merging with each other at frequencies on the order of 100 hertz. And these have been detected by LIGO. And you can see a picture of LIGO there on the right. It's an interferometer optimized for detecting gravitational waves at these frequencies. So I just want to say the really exciting thing about gravitational waves is up until we detected them, the only way we could really study astrophysical objects was through electromagnetic radiation. And they have given us a completely new way to probe properties of some of the most extreme objects out there in the universe. And we can constrain a lot of parameters about the systems using just the gravitational wave signal alone. But of course, the story gets better if you have photons and gravitational waves to work with. So now what I want to talk about is LISA and give a brief introduction. So LISA is an upcoming space-based gravitational wave observatory that's headed up by ESA now. And what I want to emphasize for those of you who aren't familiar with LISA or don't know too much about it, but have heard about it, is LISA is not just a better LIGO. LISA and LIGO are fundamentally complementary detectors because they probe different frequency regimes, and I'll illustrate this on the next slide. But just a few points I want to highlight about LISA is that it's going to revolutionize gravitational wave astronomy by probing frequency regimes we haven't looked at yet, in particular millihertz frequency regimes, as I'll illustrate on the next slide. Currently, LIGO is only really detecting gravitational wave sources in other galaxies, so extragalactic sources. The cool thing about LISA is LISA is really going to be probing our local sort of volume. Within the Milky Way, we expect to detect tens of thousands of sources potentially. And the thing I really like about those tens of thousands of sources is unlike the LIGO sources, which are transient, they merge and they're gone. The sources LISA is going to be detecting will stick around as persistent sources for hundreds of thousands of years in many cases. And that gives you time to actually follow them up with electromagnetic resources and study them and very, very precisely understand exactly what's happening in the systems. And so now to talk a little bit about the complementarity that I was alluding to. So this is what we call a sensitivity plot in gravitational waves. And what it's basically showing you is on the y-axis is a characteristic strain, which is a number that kind of quantifies how much space-time is deformed by the gravitational wave. And on the x-axis is a gravitational wave frequency, which is twice the orbital frequency since it goes as a time derivative of the quadrupole moment of the binary. And the thing I want to emphasize is those solid black lines that are labeled IPTA, ELISA, and LIGO are sensitivity curves for 3 different ways of detecting gravitational waves. And what the sensitivity curve means is basically things that fall above those sensitivity curves, those detectors should be able to blindly recover. And things below the sensitivity curve are basically in the noise for the detector. And the thing to emphasize is if you look at the curves for, I'm going to ignore pulsar timing arrays right now, which is what IPTA stands for, and just look at LISA and LIGO. If you look at their curves, they don't touch, they don't overlap. And what that means is that sources that LIGO sees at high frequencies on the order of 100 hertz, LISA is not sensitive to. But similarly, sources that LISA sees down at 10 to the minus 2, 10 to the minus 3 hertz, LIGO is not sensitive to. And so they're really complementary in that they're probing different types of astrophysical objects. With some possible overlap, some people have had ideas that merging black holes may actually pass through the LISA band and into the LIGO band. And so what I'm going to be focusing on is a particular subset of the phenomena that LISA can detect. So this plot is labeled with many different things, detectable by the different types of arrays. But the thing I'm going to focus on are the resolvable and unresolvable galactic binaries. Just a quick piece of nomenclature. What resolvable means is that LISA has the signal, gravitational wave signal from the source is large enough that LISA can individually resolve it, given its frequency resolution at that frequency. Unresolvable basically means that LISA cannot resolve the signal, and this becomes a big issue, particularly at longer frequencies, because there are so many galactic binaries out at those frequencies that if there were only 1 or 2 sources at those frequencies and nothing else in the Milky Way, LISA would actually be able to resolve it. But what happens is LISA's frequency resolution is limited and the source count is so large that they end up kind of blending with each other and actually contributing to LISA's background. But of course, in optical photons, you can still detect those sources since they're not limited by the gravitational wave detector properties in that way. Okay. And so now, just a brief introduction. I haven't actually told you what these galactic gravitational wave sources are in the millihertz frequency regime. And so now I want to give you an introduction. Most of these contain white dwarfs. And so just a brief reminder of what a white dwarf is for those of you who aren't familiar. White dwarfs are stellar remnants. Most stars in the universe will leave behind white dwarfs. Only very massive stars can produce neutron stars and black holes. And so just to give you a sense of scale, white dwarfs are about the size of a rocky planet, so about the size of the Earth, maybe a little bit bigger in most cases, but they have about the mass of the sun, so on the order of a solar mass, within an order of magnitude of that. What that means is they're really, really dense, right? Because the Earth is 1/1,000,000th the volume of the sun, and suddenly you're cramming the mass of the sun into that volume. So you're talking about something on the order of 10 to the 6 times more dense than the sun. And the other cool thing about white dwarfs is their equation of state can be approximated reasonably well as a degenerate Fermi gas. It's not a perfect approximation. In fact, a lot of my work is focused on making some of the most precise estimates of white dwarf masses and radii to actually check how well they match the expected fully degenerate relation. And there are surprising deviations in some systems, up to a factor of 2, due to other effects like mass transfer. And so something I just want to emphasize is why white dwarfs for LISA. And I'm going to show you a simple relation that kind of answers that question. So on the top here is a plot for a 0 temperature white, fully degenerate white dwarf, how its radius scales with its mass. And so the important thing to know is as you make the mass lower, they get bigger generally. And that means the density basically does the opposite. The lower the mass you go, the lower the density it gets. For most white dwarf masses we know, so between about 0.2 and 1 solar mass is the vast majority of white dwarfs, you can see that density is on the order of between 10 to the 4 and 10 to the 6 grams per centimeter cube. That's much denser than a normal star. And that's really important in understanding why they're gravitational wave sources for the following reason. So this is a relation, for those of you who haven't explored interacting binaries, that is very, very useful. It's just a simple empirical relation that applies to binaries with mass ratios of less than about 100. It's hard to get a mass ratio above 100. I mean, if you think about the sun with another object, you'd need a black hole of over 100 solar masses to achieve that kind of a mass ratio. So it's a pretty good approximation for the vast majority of binaries we know. And the relation is basically PRLO, which stands for the orbital period at which Roche-Lobe overflow occurs. Basically, matter starts flowing through the Lagrange point and accreting onto the more dense object. That period in days is approximately equal to 0.43 divided by the square root of the density of the lower density object in the system in grams per centimeter cube. It's just a simple empirical relation. And it's not always the most intuitive thing, because what it's basically telling you is if I take a star like the sun, it doesn't matter if I put it next to a white dwarf, a black hole, whatever. As long as that mass ratio is less than 100, it's going to overflow its Roche-Lobe at a period of about 8 hours. It doesn't care about the mass of the accretor. And so if you now plug in the density of something like a white dwarf instead of the sun, you see something like this. So this bottom plot, the density plot, has now been converted to the orbital period at which you would expect a white dwarf to interact, in other words, overflow its Roche-Lobe. And you can see those orbital periods are on the order of 10 to the 2 to 10 to the 3 seconds, which happens to be right around where LISA's peak sensitivity is in millihertz regime. And so that's the reason white dwarfs are kind of optimal LISA sources. Normal stars can't get down to those orbital periods, but white dwarfs can. Of course, neutron stars and black holes can as well. And so the other reason I want to emphasize the white dwarfs, though, is the vast majority of what LISA's going to be seeing are white dwarfs. So I'm certainly looking for white dwarf plus black hole and white dwarf plus neutron stars, but white dwarf plus white dwarf binaries are just much, much more common. And it's exciting because really the bulk of the 10 to the 4 sources are these double degenerate type sources. And so I just want to give you a few reasons why I think they're just really interesting astrophysically. One is they probe an interesting case of binary evolution. If you find 2 white dwarfs orbiting each other in a 20-minute orbit, you have to ask yourself, how did they get to a 20-minute orbit? And so you can probe binary evolution channels. And when you find 2 white dwarfs, there are actually a lot of things to think about in terms of their binary evolution. Like you have to ask yourself, are these 2 1 solar mass white dwarfs? Is it a 1 solar mass plus a 0.2 solar mass helium core white dwarf? Those are very different progenitor channels for getting those outcomes. And so there's just a huge diversity of evolutionary channels that you could probe by studying this population. But perhaps one of the most exciting things in my mind is actually that they're potential progenitors of type 1a supernova. And for those of you who aren't familiar with type 1a supernova, they're a very important type of explosion, which was used to basically demonstrate the accelerating expansion of the universe. This led to a Nobel Prize. And I think one of sort of the embarrassing secrets of the astronomy community is, although we all pretty much agree that type 1a supernova come from the explosion of a white dwarf, there's still no real consensus on what the progenitor or progenitors are. So there are kind of these 2 generic models, the single degenerate channel, where you basically have a white dwarf accreting from a main sequence star like the sun. It goes over the Chandrasekhar mass thanks to the mass it gains through accretion and then explodes. And then there's the double degenerate channel in which 2 white dwarfs, each of which are under the Chandrasekhar mass, merge, and that actually triggers a type 1a supernova. And in my mind, at least, the double degenerate channel is becoming more and more popular. But the thing is what would be really exciting is to actually find a progenitor of a type 1a within the Milky Way. And so if you take nothing else away from this talk, I want to emphasize, I think this will be one of the coolest results to come out of LISA when it launches. When LISA launches, think about this. We're overdue for a supernova in the Milky Way right now. There should certainly be another Type 1a within the next century. When you talk about white dwarfs merging within a century, the kinds of orbital periods you're talking about them being at now are really at about a minute or less. LISA is very, very sensitive to those frequencies. And what that means is when LISA turns on, it will be able to tell us exactly where and when the next Super Chandrasekhar white dwarf merger will occur in the galaxy. Should be able to with very high signal to noise and even tell us the distance to the source. I think that will be really cool. And if we're lucky, it may even be within a decade or two. And we'll actually be able to build follow-up resources and study the progenitor and actually watch it go through the merger and explode. But I think that will be one of the biggest results that will come out of LISA. And it's pretty much a guaranteed result because of LISA's sensitivity at those frequencies. And if those merge and don't produce a Type 1a, it will also be able to answer the question, do these produce a Type 1a or not? If they don't, we know this isn't the progenitor. If they do, we've actually got definitive evidence. Okay, so I want to shift gears now to the optical photometry part of the talk, which is actually what I work on. So I don't actually analyze any gravitational wave data because LISA's still 15 years away. What I do is work on a survey based at Palomar Observatory, and that's what I'm showing a picture of here. And so that big telescope in the foreground is the 5.1 meter Hale telescope, which has been one of the most scientifically impactful telescopes in history, I think. It's done a lot of amazing things. And even though it was built in the 1940s, it's still doing amazing science. I use it quite a bit. But the real star of the show I want to emphasize is actually another telescope that was built a long time ago, even older than the Hale, and that's that little 48-inch Samuel Ocean Schmidt telescope you see on the left. And what's so special about that telescope is even though it has a very small aperture compared to something like the Hale telescope, it has a very large field of view in its focal plane. It's 47 square degrees. And the instrument that's currently mounted on it, the Zwicky Transient Facility, is basically a camera that was built, designed to leverage that full field of view in the focal plane. And so it images 47 square degrees in a single exposure. And just to give you a few survey parameters for those of you who know a little bit more about optical surveys, the exposures are 30 seconds, so it has fairly high temporal resolution. It uses 3 filters, GR and I, and it has 1 arcsecond pixels, which slightly undersample the typical point spread function you get at Palomar, which is 1.5 to 2 arcseconds. But the crucial thing about ZTF compared to a lot of other surveys of similar depth or deeper is that it has the large field of view and it can accumulate a lot of images quickly. And what do I mean by that? So I'm comparing here on the right ZTF to a lot of other big public wide field of view optical surveys that are either currently online or will be coming online. And the main comparison I'll draw is to LSST, now known as the Vera Rubin Observatory, which has a much larger collecting area than ZTF, but about a quarter of the field of view. And so the big thing about ZTF versus LSST is even though LSST is probing a much larger volume with each exposure because it goes so much deeper, it accumulates epochs at a much slower rate. So in 10 years, LSST will accumulate about the same number of exposures as ZTF did in 2.5. And the reason that's a big deal for this particular type of science is the way I find these short period binaries is I basically look for periodic flux variation. So every time ZTF takes an image, it basically gets a flux measurement of all of the stars in that image. And because it's doing this repeatedly, you get very well sampled light curves. And these binary systems that are millihertz gravitational wave sources vary their flux periodically on their orbital periods. And so the key is with something like LSST, you can detect these types of signals because it's randomly sampled data. The problem is these short period binaries are merging due to gravitational wave emission. And that means that their signals are actually not coherent even on multi-year time scales. They decohere quite quickly. And that means you need to do something called an acceleration search to basically account for their orbital decay in order to detect them with a survey like this. The good thing about a survey like ZTF, and Optical also does this really well because of its observing strategy, is what you really want to do is get in as many exposures as you can in a short amount of time so that you don't have to worry about the effects of orbital decay, and you already have enough data to just detect the signal based on the period. And so deep drilling experiments like those ZTF and some other surveys have done are actually the optimal way to detect these. And it will be challenging with LSST because even though there may be sufficient data to find them, the coherence timescales will just be too short compared to how long it takes LSST to get that data. So I made this sound easy, just look for periodic flux variations, but there is a technical challenge. And I spent a lot of my PhD thinking about this. And that is the following. Period searching is an old business. There are a lot of great algorithms that have been developed to look for periodic signals in light curves. Lum-Scargill is perhaps one of the most well-known. AOV, Boxley squares, there are a lot of different variants, and they're all very good in their own way. But one of the challenge is the following. If you want to go to very short timescales, say minute periods, in data that's been sampled over the course of years, you need a very large frequency grid to search, on the order of 10 to the 6 to 10 to the 7 frequencies. That's manageable if you're working with on the order of a few 100,000 sources, but if you really want to do a systematic search of, say, 1 billion light curves, which you actually have access to as something like ZTF, because it's all sky and goes down to 21st mag, you have to rethink how you do this. And so I spent a lot of my PhD thinking about how to just find and implement the fastest variants of these period finding algorithms. And GPUs turned out to be a very useful tool for this. And you may ask the question, well, why do you need to search 1 billion sources? We have Gaia, we can pick out white dwarfs pretty well. Why don't you just pick out the 500,000 white dwarfs and just search those? And the answer is I do that, obviously. But there is actually value in systematically going through the 1 billion sources, including the main sequence. And that value is this short timescale phase space has not really been systematically explored, especially not on an all-sky level. And the reason is the computational limitations. And beyond just thinking about the short period binaries, there are other amazing phenomena that live in this corner of phase space. An example I'll refer you to is AR-SCO, which was the first white dwarf pulsar, which actually is a main sequence star with a white dwarf companion that's rapidly rotating, which basically doubles its brightness on minute timescales. It was actually identified by amateurs. Those sorts of signals, if you look only at the white dwarf track, you would never find that type of object. So I think there's actually a lot of rich science to do by more systematically exploring this phase space. And in the modern era, computer hardware is actually enabling us to do this, where before it was impossible. And so now I want to shift gears to talking a little bit more about the science and less about the nuts and bolts. So to talk a little bit about this new corner of phase space that I'm exploring is, I've already found over 1,000 objects which definitely exhibit astrophysical periodic flux variations at periods under 30 minutes. The ones I'm most interested in, which I'm going to focus on for the rest of the talk, are the new detached and accreting double degenerate sources, so those gravitational waves sources I was alluding to. But I want to emphasize there are a lot of other interesting sources in this regime. Some of those include intermediate polars. Not many of those are known. Those are magnetic white dwarfs accreting from a main sequence star, where basically the white dwarf gets spun up by the angular momentum it's gaining during accretion. And so they can have rotation periods on the order of minutes, and you actually get a photometric signal on the rotation period of the white dwarf due to a hot spot going around its surface. They're also what I call vermin of the sky because they're my most annoying false positive because they show periodic variations down at minute orbital periods, or minute periods, not orbital periods. They tend to be blue and look like white dwarfs because often the main sequence star is a cool M dwarf and the white dwarf is dominating. They can be X-ray, they usually are X-ray sources, and so they can look a lot like an accreting double degenerate or ultra-compact X-ray binary. And so they masquerade as these. They can have outbursts and things too. And so the real only definitive way to rule out an intermediate polar versus double degenerate is to get phase resolved spectra and check for things like radial velocity variations on the orbital period and whether there's hydrogen or only helium in the system. And that's very expensive follow-up to get. So those have actually been some of my most troubling sources, even though scientifically they're also very interesting. Some of the other sources which are interesting in this phase space are pulsators, like ZZ SETIs and DB white dwarf pulsators. Those are two types of white dwarf pulsators. Also SDB pulsators, P-mode pulsators. These all pulsate on minute timescales. They're very interesting objects for a field called astroseismology. And then the last class of sources I just want to briefly mention is I've been discovering a lot of highly magnetized white dwarfs, which show rotation periods on the order of minute timescales. And we actually have a very exciting paper coming out on what looks to be the most massive white dwarf known, which is rotating on a 6-minute period. It also has one of the most magnetic, or is one of the most magnetic white dwarfs known, with a surface field of about 800 megagauss. And we think it may actually collapse into a neutron star. So these aren't binaries, but there's just a lot of other rich science in this phase space. But now I'm going to shift gears for the rest of the talk to what's near and dear to my heart, and that's the gravitational wave sources I've been finding. So here are follow-up light curves. So these are not ZTF light curves. These are follow-up light curves of 15 sources I discovered using ZTF, and one of them was discovered with its predecessor, the Palomar Transient Factory, PTF. So those periods you see above the plots are the orbital periods of each of these systems. They're sorted by their orbital periods. And so the thing I want to emphasize is there are really two main sources of photometric modulation in these binaries. There are eclipsing sources, and the example I'll point you to for that is the 23.7 minute system there in the left-hand column. And then there are what we call ellipsoidal variables, and the example I'll use for that is the 20.6 minute system there towards the upper right, the more sinusoidal looking one. And let me explain just physically what actually gives rise to that flux variation. In the case of eclipsing sources, it's pretty straightforward. There's an occultation at what we call the time of superior and inferior conjunction. Basically, one object passes in front of the other. When that happens, flux goes down because the object is blocking light from the other object. And so basically with any eclipsing source, you have two eclipses per orbit, and their relative depths tell you something about the relative temperatures of the two objects involved in the eclipse. And you can see the little movie in the lower left-hand corner just kind of gives a basic illustration of what's actually happening and corresponding to the flux modulation in the light curve. But the more complicated one to understand that I want to draw attention to is the plot on the right and the movie on the right, the ellipsoidal variable. So that's more sinusoidal variability. And what that is arising from is the following. When an object that's contributing most of the luminosity in a binary is being tidally deformed by its companion, what ends up happening is you get a flux modulation at twice the orbital frequency for the following reason. You're seeing different geometric cross sections of that deformed object over the course of an orbit. So you can basically assume it has about uniform surface brightness. There are deviations from that due to things like gravity darkening, but it's a decent approximation. And so what you see over the course of an orbit is a change from the egg-shaped cross-section to the circular cross-section, back to the egg-shape, back to the circular. And that gives you the twice per orbital frequency modulation. Those sources are not as useful for parameter constraints. Eclipsing sources are very valuable because you get radius estimates, very precise inclination constraints, etc. But the ellipsoidal sources are something I refuse to ignore for the following reason. If you ever want to find a black hole or a neutron star with a white dwarf companion that's detached, and you looked only for eclipsing sources, you would never find one. You would need to look for ellipsoidal sources to identify such a system. And even though the inclination constraints are limited on them, they still need to be reasonably near edge on to get large-scale modulation from ellipsoidal modulation. It is still inclination dependent. And more critically, LISA is going to be very, very good at measuring inclinations. And so all of these ellipsoidal variables we find now, LISA will give us the critical piece of information to be able to translate the radial velocity semi-amplitude we measure on them into a mass function. Okay, so that's just some of the physics behind what actually gives you the flux modulation in the light curve. But I want to emphasize another important part of the program is getting follow-up spectroscopy. This is very challenging with these sources, and I'll explain why. But just for those of you who aren't familiar with spectra of white dwarfs, I just want to kind of give a brief overview of what you're looking at. So you're looking at spectra for those 15 sources now. And so kind of the most common type of spectrum I'm used to looking at is, again, I'll use the 23.7 minute system there on the left as an example. This is a DA white dwarf. So it's a white dwarf with a hydrogen envelope on it. So you see broad Balmer absorption lines. That's actually, most of these systems are actually double lined, which means you actually see lines from both white dwarfs. The reason it's challenging to measure things like radial velocities in these systems is because the radial velocity shifts, even though they're on the order of a few hundred kilometers per second, white dwarf lines are very, very broad. They're 50 to 100 angstroms across. And so the Doppler shifts you get are actually quite small compared to the full width half max of those lines. There are NLTE cores, is what we call them in the white dwarf lines, which are much narrower. But the problem is you need very, very short exposures to not smear over the full width half max of those lines in these systems because of how quickly the Doppler shifts are evolving. You're talking about Doppler shifts of over 1 kilometer per second every second of orbit that elapses. And so your full width half max gets washed out very, very quickly if you don't have very high time resolution. The other class of sources just in these spectra I want to mention is that you see some sources with lots more lines, absorption lines. Those have helium-enriched atmosphere. So basically, there's not much hydrogen remaining on the atmospheres for a variety of reasons. And then there are also accreting sources like you see those in the central column. Those are what we call AMCVNs. It's basically one white dwarf accreting from another. And so I just want to emphasize the technical challenge here, and the reason I'm leaning less and less on phase resolve spectroscopy is the following. The 7-minute binary you see in the upper left-hand corner as an example I'll use is, if you want to get phase resolve spectra, you need your exposures to be much shorter than your orbital period. For something like a 7-minute binary, that means sub-minute exposures. These objects are faint. They're fainter than 20th magnitude for the most part. Even a 10-meter class telescope has a hard time getting over the read noise floor on most spectrographs because you're dividing your photons when you take an exposure that short on something that faint. And it's still doable right now with 10-meter class telescopes if you're willing to spend enough hours on it to coadd a signal over the noise floor. But in the LISA and LSST era, I think this will become impossible, even with 30-meter class telescopes, especially since we're going to be finding shorter and shorter period systems using something like LISA. And so what a lot of my work is focused on is instead making use of the rich information encoded in the light curves themselves. And what I hope to convince you of with the rest of this discussion is how valuable light curves are in physically characterizing these types of systems. And the example I'm using here is a light curve taken with an instrument called HyperCam, which is a high-speed photometer based on the GTC. It's the only high-speed photometer, to my knowledge, on a 10-meter class telescope. And this is of the 7-minute orbital period binary found with ZTF, which is the shortest orbital period eclipsing binary known. And so I just want to point out a few things you can learn just by looking at the light curve. So a few things that most people's attention are drawn to almost immediately is it has a remarkably deep eclipse. It's a total eclipse. And there's actually a shallow secondary eclipse as well, though that eclipse is not of any intrinsic luminosity of the secondary, but rather just the irradiated face of that object. And the quasi-sinusoidal modulation you see out of eclipse is because one of these objects is heavily irradiating the other, mainly in the ultraviolet. And so what I want to show you is all the physical parameters you can actually infer about a system like this just by looking at the light curve without even doing any analysis. One is, the inclination has to be close to 90 degrees or somewhat near adjacent, right? Otherwise, it wouldn't be eclipsing. So the eclipse tells you something about the inclination almost immediately. Another thing you can reason is because that primary eclipse is very, very deep, that object is contributing much more luminosity than its companion. What it actually translates into is the ratio of the depths of those eclipses tells you something about the surface brightness ratios of the two objects. Basically, how much flux in this passband is coming off per unit surface area on each of these white dwarfs. And so that in turn tells you the ratio of the temperatures of the two objects. And what it's telling you is basically object 1, which is being eclipsed in that total eclipse, is much, much hotter than object 2. You can just reason that out by looking at the eclipses. The other cool thing you can reason is the following. That eclipse is total. It goes to basically zero flux. And what that means is this hotter object, object 1, is being completely occulted and blocked by object 2. That immediately tells you object 1 needs to be smaller than object 2, otherwise you wouldn't be able to completely block it. So you can immediately reason that R1 is less than R2. And then finally, using the white dwarf equation of state, you can immediately reason that mass of 1, that smaller object, must be bigger than mass 2, the bigger object, because we know that the more massive you make a white dwarf, the smaller it gets. So these are just inequalities and statements you can say about the system just by looking at the light curve. But of course, if you actually fit a model to it and analyze it, you can make very precise estimates of all of these quantities. And so, in my opinion, light curves are perhaps the most powerful analysis tool we will have for the gravitational wave sources LISA detects. And of course, LISA will give complementary information in that it will be measuring things like the inclination independently using gravitational waves. But some things in gravitational waves, you just can't do in gravitational waves. For example, temperatures. Gravitational waves are never going to tell you anything about the surface temperatures of these objects. That's a uniquely optical phenomenon to probe. And the other cool bit of physics you can actually probe with a light curve like this is the following. In this particular system, the cooler object, which is a helium core white dwarf, is only about 5,000 degrees. And we were able to measure this by actually detecting the object in the bottom of the eclipse. This is not trivial because this system gets down to about 28th apparent magnitude in its primary eclipse. The bottom of the eclipse lasts less than 10 seconds. So to actually resolve it, we needed to take 3-second exposures. Even on a 10-meter class telescope, 3-second exposures at 28th magnitude are not getting you a lot of photons. So this is not an easy feat. But that temperature measurement told us something very, very interesting. And that's because I've worked with an expert on tidal physics in white dwarfs while I was at Caltech, Jim Fuller, and he predicted that that object should be tidally heated to about 15,000 degrees in this binary. I don't need to tell anyone here, a 5,000 degree black body is outputting a lot less energy than a 15,000 degree black body. So there's a huge discrepancy in the energy budget we actually see being output by the source versus what we predict tidal dissipation should be generating. And so it's starting to challenge some tidal models in white dwarfs already. The other really cool thing you can do with a light curve is the following. You can time the time of superior conjunction very, very precisely in eclipsing sources, and you can even measure it reasonably well in ellipsoidal sources. And what that means is the following. If a binary is not changing its orbital period, you expect the eclipse to always happen at the same time you predict. Say the orbital period is 6.9 minutes, like that object in the upper left-hand corner. That means if you measure one eclipse and you know when that eclipse happened very, very well, you should expect every subsequent eclipse to happen exactly 6.91 minutes after it. But what you can do is you can continue to measure the eclipse time and look for deviations from that. And the idea is if the orbital period is shrinking or increasing at a constant rate, you expect those deviations to accumulate in a quadratic fashion. With concave up for increasing period, concave down for decreasing period. And all of these systems are exhibiting concave down because they're all undergoing rapid orbital decay due to emission of gravitational waves. And And so we've actually measured that, and that lets you do something really cool. It actually lets you estimate the energy loss due to gravitational waves in these systems and compare it to the prediction due to general relativity if you have an independent mass measurement in the systems. And one does actually expect discrepancies in these cases because of things like tidal dissipation. I just want to mention these plots are analogous to the result that won the Hulse-Taylor pulsar, which is a binary neutron star, the Nobel Prize a few decades ago. The difference is the orbital decay is much more extreme here. So to give you an idea, the Hulse-Taylor pulsar had a deviation in its phase on the order of 40 seconds after about 20 years or so. The 7-minute binary has a deviation of over 2,500 seconds on the order of less than 10 years. And you may pause and say, wait, 2,500 seconds is more than 7 minutes. What it actually means is basically the system has skipped several orbits compared to a system that is not changing its orbital period. And what these measurements actually let you do is estimate the chirp masses of the systems, which lets you estimate the gravitational wave strain of them, and put them on a LISA plot, which you can see there on the right. They've been color-coded according to each of those systems. And I just want to emphasize this LISA plot you're looking at is the almost full sample of ZTF binaries I've discovered so far compared to the LISA sensitivity curve, which is that black solid line. So things falling above it in general, LISA would blindly detect. And so I kind of want to wrap up the talk to talk about how this has changed the landscape of LISA over the last 2 years. So the plot you currently see were all the known sources as of 2 years ago, almost 3 years ago now, published by Kupfer et al. In 2018 after Gaia came out, using basically the distances. He inferred the gravitational wave strains of the sources. It took decades to get to these. And something to emphasize is out of these sources, most of them were accreting outbursting sources. Only 2 were eclipsing. And I hope I've convinced you in the discussion of light curves how valuable eclipsing sources are. So this is what CTF has added in the past 2 years. This is the sample I've discovered and shown in red. In that time, I'm only aware of one confirmed binary, which will be LISA detectable, discovered by another group, and that's the Brown et al. Discovery of a double helium core white dwarf, which is actually quite nearby, shown in magenta. But the cool thing about the ZTF sample, so one, ZTF is dominating this field right now, obviously. We're churning out a lot of these, and there are a lot of new discoveries coming in. But the really cool thing about these discoveries is the more I follow them up, the more I realize almost all of these show some signature of eclipsing behavior. And that is not surprising for the following reason. There's a selection bias here when you're looking for photometric variability that favors near edge-on systems, even with ones that are primarily ellipsoidal modulation. And I think that selection effect is showing itself here. That's bad news for gravitational wave detection, though, because edge-on sources are actually less loud in gravitational waves than face-on sources. And the thing I want to really leave you with as a point is a lot of people have been asking me, well, now that you have such a big sample, you can start to do population work and estimate rates and probe evolutionary channels. And I thought that too 2 years ago. The problem I'm running into is it seems like every system I find here is different and unique in its own way. They're like snowflakes or something. They don't fit into neat evolutionary pictures, and there's a huge diversity among them. And I'm just going to show you a few of the shortest period systems to illustrate the sheer amount of diversity, just going through these one by one. So the 2 shortest period eclipsers, which I just labeled, are 2 eclipsing pairs of eclipsing double white dwarfs. One is a helium core plus a carbon-oxygen core. The other is a helium core plus a helium core. Those come from very different evolutionary channels. So even the diversity among the 2 shortest period eclipsing sources, very different types of sources. Now we look at this one down here, which is lower strain. That's the shortest period AMCVN with an accretion disk. No one's ever seen one below 10 minutes. We think that means it comes from a different type of evolutionary channel than the other AMCVNs. It's maybe the first of its kind. That's very exciting too. The next shortest period system is actually a white dwarf plus a hot subdwarf accreting onto it. Again, totally different scenario, lots of rich possibilities to be probed there. I could keep working my way up in period and tell you a story like this for pretty much every single one of these sources. And the point I want to get across is even though we have a decent size looking sample, the phase space is just too high dimensional. This is so rich. And it makes me really excited because I can only imagine when Lisa gives us 10,000 of these, all of the things we're going to find. And so now to conclude the discussion, just looking to the future, I want to talk a little bit about what I'm thinking about doing in the future. One is I've only done this on ZTF, but I've built up a lot of machinery for probing this phase space that is applicable to other time domain surveys. And so some of the ones I plan on immediately going after are ones that are publicly available anyway and easy to get to, like TESS, which is already producing a lot of wonderful data. LSST, which will be coming online soon and go very deep. Gaia, which will be releasing its time result photometry relatively soon, etc. I mean, this field is exploding. There's so many time domain surveys now. It's very, very rich. And I think over the next decade, we're going to see a lot of exciting stuff in this phase space. Some points I want to leave too, though, is that it would be nice to get more high-speed imagers optimized for following these systems up in the future. We currently have one on a 10-meter class telescope, and it's only mounted a small fraction of the time. That's HyperCam. It would be nice to get more of these on 10-meter class telescopes to follow up LSST sources and the near LISA sources. But more critically, it'd be nice to get one of these on an ELT, either GMT, TMT, the European ELT, because when LISA turns on, some of the most exciting sources it will find will probably be 20, 30 kiloparsecs away. And you really need a 30-meter class telescope if you want to take short exposures on that and actually look at the 1A progenitor and photons before it explodes. And the last thing I want to mention is finding these right now and not waiting for LISA is actually very useful because we can start monitoring them for orbital evolution. And so by the time LISA turns on, we'll have very, very well measured orbital decay rates, and in some systems even the second derivative of the orbital evolution, p double dot, which tells you a lot about effects like tides and mass transfer, etc. And I know I'm running out of time, so I want to wrap up here. Thank you for inviting me, and thank you for your attention.
Right. Thank you, Kevin. I'll do the clapping on behalf of everyone. Thank you for this entertaining talk. If there are questions to Kevin, please raise your blue hand, and I see already many. Marius was first, please.
So, hello, Kevin.
Hi.
If it is with LISA, we'll be able to detect the wide draft dwarfs. So it is some small black holes, but it is a little bit heavier than neutron stars. So for LISA sensitivity, it is no way for escape with small mass black holes if they are in our Milky Way galaxy. So all they are will be detected if they have if they are in some binary system.
Yeah.
Yes?
Yeah, I believe so.
Believe so. Okay, yeah. That's what I wanted to ask you. Thank you.
Yeah, in general, binaries, yeah. That'll be interesting to see what LISA finds in terms of binary black holes in the galaxy and binary neutron stars. The challenge is they still need to be pretty short period, so under about an hour period. And the merger time scale at that point for objects like that is on the order of tens of mega years. So I think we'll be lucky if we even find a few in the entire Milky Way, just because they don't live that long by the time LISA can see them.
Okay. Okay, thank you, Kevin.
Milena was next.
Hello, hi, very cool. Well, not literally, but very nice stuff. I have two questions. One is, when you work on timing of eclipsing, well, let's say binaries, have you found any triples, any like systems with the triple body, so the changes of the period that give you the information about the third body? And the second question is about the test cadence. So I believe most of the tests available cadence are 30 minutes, and I guess this is not enough for your studies. So can you comment on that?
Yeah, so I'll start with the triples. I'm definitely looking for them. So I'm monitoring all of these sources. So far, they're all behaving kind of what you expect from gravitational wave decay. But it's possible some of the longer period sources may show some kind of timing residual associated with a third companion. I have, however, identified triples using Gaia. I already have a system or two actually in a wide hierarchical triple. And the association is very clear, not because of the parallax, but because the proper motion matches very, very well. So for many of these sources, the parallax is negative. It's not well measured because they're so faint. But the proper motions are still measured exquisitely well, and you see, okay, these match too precisely. That must not be a coincidence. For tests, yes, the cadence is a challenge, but things are getting better. So on the long period end, the 30-minute exposure can still be okay for getting systems sort of on the order of an hour period, but not very useful for minute periods, obviously. TESS is now doing 10-minute full frame images, though, in its latest run. And that is a much better story already. And there's talk about going even shorter, potentially down to 6 minutes. And by the time you get down there, you're actually in a pretty good place because TESS's limiting magnitude is so bright that you actually don't really expect many 5-minute binaries that TESS would be able to get reasonable flux for anyway. So you can kind of systematically explore maybe down to about 10-minute periods for everything brighter than a 19th or so. And I want to emphasize, I have actually checked this. TESS can go surprisingly deep if you bin data. Their signal to noise and individual exposures may not seem great, but it's amazing the signals you can pull out when you bin the data. And the example I've used is 2-minute cadence data on objects that are 18th or 19th magnitude showing total eclipses. You can very, very clearly see the signal in the 2-minute cadence data. So I think TESS is kind of underappreciated in what it can do because most people think, oh, it's only very bright sources. But you can do surprising things if your period is short enough that you have enough orbital cycles over the course of a sector.
Okay, good hint. Thank you. Good luck.
Okay, the next is Przemek.
Hi, Kevin. So I was wondering how distant sources are you detecting, and how distant sources can be detected with LISA?
Yeah, so currently the most distant sources I'm finding are on the order. Actually, I have one that's at like 5 or 6 kiloparsecs. Those are the very luminous ones, like the AMCVNs are accreting helium stars. For double white dwarfs, especially the shortest period ones, it's more on the order of 1 to 2.5 kiloparsecs is kind of the range. The 7-minute, I quote 2.5 kiloparsecs. LISA will blindly find binaries like the 7-minute at a distance of about 30 to 50 kiloparsecs, so much larger volume. If it went even a bit shorter periods, say down to 4 or 3-minute orbital periods, you would see them in the Magellanic Clouds. And so part of the challenge is if you take something like the 7-minute binary, which is not reddened, is apparent magnitude of about 21, and now put it at 30 kiloparsecs instead of 2.5 kiloparsecs, the follow-up resources you need to actually see it in the optical become much more challenging. And so that's why I was talking about the need for 30-meter class telescopes and high-speed imagers.
Yeah, thanks.
Right. So I have a question. Maybe you said that, maybe I missed it. So what's your brightest target?
The brightest is actually 15th. It's surprisingly bright.
Yeah, so that's fairly bright. So you can actually achieve that with smaller telescopes, and they have plenty of time, and they can do fairly high cadence. I don't know if it's quick enough.
Yeah, so those are definitely easy, and we've actually been following them all up. My worry is the most exciting systems, like that Type 1A progenitor that may go off 10 years after LISA launches if we're lucky. That's probably going to be like 5-10 kiloparsecs in the way, probably in the plane behind some dust. And what you really want is something on like the ELT, an infrared imager that can actually get through the dust and get a light curve of it, because it's going to be horribly faint. But it's still doable. You can actually see them surprisingly far away with something like a 30 or 40 meter class telescope. So it's not that we can't do the bright ones. I'm just worried about the exciting science we may miss out on by not having any capabilities to do the most faint ones.
True. And I have another question related to Gaia. You said you'll be using Gaia photometry. And how about Gaia astrometry? Is that of any use, given the low cadence? But still, if there is any astrometric displacement, have you thought about detecting this?
Certainly for wide binaries, yes. But for the problem with the LISA ones is the orbital periods here are very short. So the semi-major axes, the 7-minute binary, that entire binary, you can fit inside the planet of Saturn. That's how small it is.
It's not that small. If it's close enough, then maybe.
Yeah, but most of these systems are kiloparsecs away. So the astrometric wobble you're actually talking about is tiny. So the problem is these are just so close. But certainly Gaia astrometry has been very powerful, as I mentioned, for identifying potential hierarchical triples. And I think a lot of people who've been looking for them have maybe not been paying so much attention to common proper motion, have been focused on common parallax. But proper motion is going to age much better than the parallax measurement. And it's a very powerful tool, I think, for these sorts of things.
Great, thanks. Any more questions? I see Mariusz Gromacki has a question in the chat. Mariusz, you can read it.
Okay. So I would like to not unmute because of my kids. So I would like to ask what will be the size of the detection. It will be problem to easily find the counterparts for the the LISA detection size.
Yeah, so I actually don't exactly know the answer to this. It's very sensitive to signal to noise ratio. I believe a number I've heard quoted is typically on the order of arc minutes. And so something I'm thinking about, for example, is say you have a LISA source with a few minute periods and a few arc minute localization. You can do the following exercise. You kind of know the distance based on the LISA strain, and you know the source must be very blue. Binaries with these kinds of short periods are never red because tidal heating heats them up. If they're accreting, they get dominated by an accretion disk. So what you do is you take something like LSST, which goes very, very faint, and you just look for all of the blue sources in the localization circle. And you can do even better because LSST will actually measure some parallaxes. They will not be as precise as Gaia, but they will be very good for things like white dwarfs, which are too faint for Gaia, but still have intrinsically large parallaxes because they tend to be more close by. So I think LSST's archival data may actually prove one of the most powerful tools in identifying which of these things in the LISA error circle is actually the source of gravitational waves. But there may be some high-speed imators you could build with a large enough field of view that you could just image the entire error region and then see which source is actually oscillating at this orbital frequency.
Thank you very much. It sounds very reasonable.
Okay, great. I don't see any more questions to Kevin. So thank you very much, Kevin. That was really fun to see and to learn a lot. So thank you for this. Enjoy the rest of your day and, future, whatever comes soon. Thanks for joining us here. And I thank everyone else for joining. And I just remind you that next week there is no seminar because we are still in the holiday mood of Easter here. So I'll see you in 2 weeks' time. Thank you all and goodbye.
Thanks. Bye.
Thanks. Bye.